Section 2, Stationary waves. Here we'll be making use of the principle of superpositions to explain how standing waves are formed. Okay, to do that we are going to look at the Java applet. This one I've chosen to be a fixed end. So we will start the animation. So by sending a wave in the medium, okay, we can take this to be the string. All the black dots here that you see represent the particle on the string. So by sending a wave, the particles are being displaced in the string. So we have a progressive wave. To get a stationary wave, we need two identical waves traveling in opposite direction. So the best way is to have the incident wave reflected. So as you can see, the blue wave is the reflected wave. So this section now have stationary wave. Okay, let's pause. Okay, so you see that the reflected wave now, I have 1.5 wavelength. Okay, until here. So this part of the wave, you actually apply the principle of superposition. Like this point, for example, you take the displacement of the blue wave, which is the reflected wave, plus the displacement of the incident wave. So the resultant amplitude is here, which is the maximum displacement at this instant, okay, for the resultant waveform. Okay, let's continue. So slowly we are getting the stationary wave in the whole of this section of the string. If we were to look at the black wave, which is the stationary wave, it does not progress forward. Okay, so all it does is to vary from the maximum displacement to 0, and then to negative displacement, maximum amplitude, and then back to 0 again, and maximum positive displacement. So by having two waves that are identical, traveling in opposite direction to overlap, we get a stationary wave. Okay, so I think we have seen enough. So now we move on to discuss about the characteristics of stationary wave. There are 6 of them. The first one is about the wave profile. It does not progress. So as you can see in the animation here, the stationary wave basically, okay, what I like to say, open and close. You move from maximum to minimum, maximum to minimum. If it's fast, you will see loops. Okay, but this is quite slow. Then what happened to the energy? Because the wave does not progress, so we don't see the energy being transferred from one point to another. Instead, all the energy is trapped within the wave. Okay, the next thing I would like you to observe will be the particles. Notice that the particles between two nodes, right? Between successive two nodes. Okay, all these particles here, they move up together, down together, to the lowest point, back to equilibrium, and up together. So we say that they have the same frequency. All the particles have the same frequency, except the nodes, because they are not moving. Okay, similarly, the particles here we can see also, they move up together, down together. At one instant of time, they move to equilibrium together. At this instant of time, they actually all go to the maximum displacement. Okay, I should put it here. Then this instant of time, they are almost back to 0. At this instant of time, they almost reach their maximum. Back to 0. So the time taken for them to complete one oscillation, that is to go from maximum back to equilibrium to the other end, and then back to the same point, the time taken, the periodic time is the same, and therefore they have the same frequency. The amplitude varies. Notice that the particle here, okay, this one in the middle, it has the maximum amplitude, whereas the particle somewhere here, the amplitude is smaller, and at the nodes the amplitude is actually 0. Okay, the particles that have the maximum displacement or maximum amplitude, we call it the antinode. The fifth characteristics will be particles in the same loop. Okay, between successive nodes, you can see all the particles, they have the same phase. So if you were to imagine all these particles being in the circle, okay, all of them will be at the same part of the circle at the same time. Whereas particles in the adjacent loops, okay, or the alternate segment, they are out of phase by 180 degrees. So for a stationary wave, the particles are either in phase, that is phase difference 0, or they are 180 degrees out of phase. They won't be 90 degrees, 270, or any other angles out of phase. Okay, the last characteristic will be the distance between successive nodes or successive antinodes. They are exactly half a lambda. Okay, because we saw how a standing wave is formed, right? From here, okay, you follow me, to here, this is exactly one wavelength of the incident or reflected wave. So this consists of 3 successive nodes. So the distance between 2 successive nodes will be half lambda, or the distance between 2 successive antinodes will be half lambda also. Okay, the next part we're going to compare the characteristics of stationary wave and progressive wave. In your lecture notes, right, you can actually find on page 4 a table. You can take some time to complete the table now. Pause for about 5 minutes. Okay, there are 6 characteristics for stationary waves. So in the table, you should see 6 rows. The first one is amplitude. Amplitude will be the same for all points for progressive wave, but that for the stationary waves, it will vary. Largest at the antinode, 0 at the node. Frequency, same for both, whether you're talking about stationary or progressive waves. But at the node, the frequency is 0 because they are not oscillating. So that is one difference between the frequency of stationary waves and progressive waves. Okay, next we look at the wavelength. For progressive waves, it will be distance between 2 points or 2 consecutive points that have the same phase. So it's exactly 1 lambda apart. But for stationary waves, it will be twice the distance between successive nodes or antinodes. For phase, progressive wave, all the particles within one wavelength will have different phases. Whereas for stationary waves, within the same loop or same segment, they all have the same phase. The alternate loop will have a phase difference of 180 degrees out of phase. 180 degrees out of phase. For progressive wave, there's a formula to calculate the phase difference. You take the ratio of the path difference over the wavelength times 2 pi, or you can take the ratio of the time t over the period times 2 pi. But there's no such formula for stationary waves. Then for the waveform, progressive waves, the wave travels in the direction of the wave, but stationary waves does not progress. Energy for progressive waves is being transferred from one point to another, but for stationary is being trapped in a wave. Okay, we have been discussing about how a standing wave is formed, as well as the 6 characteristics. Well, this is an animation here that show you the stationary wave for longitudinal as well as transverse. For longitudinal, notice that at the antinodes, right, the particle also have maximum vibration, and at the node it is not displacing. For transverse, this one we're very familiar with. Okay, you have maximum displacement at the antinode. Notice that the difference between these two, right, transverse and longitudinal, is the way the particles are vibrating. Other than that, they look exactly the same. So if I were to sketch the displacement versus distance graph for transverse wave, it will be the same as the displacement versus distance graph for a longitudinal standing waves. In the lecture, I demo the stationary wave using a slinky. So I will put that in the enrichment activity for next year. You can try that. So here I'm not going to show you the demo. Okay, so we take a look at the transverse wave formed in a string. Okay, similar to what you will see in the slinky. For two ends fixed, the lowest frequency that you can get will be when the length of the string equals to half lambda. Okay, you cannot go anything lower than that with a vibration that have two ends fixed. So we call this mode 1 or the fundamental frequency. Okay, for those who learn music, we also call this the first harmonic. Then the next lowest frequency, we call it mode 2, will be when the length of the string equals to the wavelength, lambda. And then we can go higher. Mode 3 will be when the length is 1.5 lambda, and so far so on. So we can see that what happened here is there is a different mode of vibration. So as the frequency go higher and higher, the wavelength actually become shorter and shorter. Okay, with that, let's take a look at example 2. So you can take 5 minutes to try this question. We pause here. Okay, in this example, you're given a wire 1.2 meter long, fixed at each end under tension. So a transverse wave of speed 300 meters per second is propagated along the wire and forms a standing wave pattern by reflection at the ends in a certain mode of vibration. So you are not told whether it's mode 1, 2, 3, 4 or any other number. It is found that the nodes are 0.4 meter apart. So nodes are 0.4 meter apart, meaning half lambda will be 0.4. What is the frequency of this mode? What lower frequencies are possible? So the strategy to solve this question, right, is to draw a diagram. The wire is 1.2 meter, node to node is 0.4. So if I take 1.2 divided by 0.4, I will have 3 half lambda. Okay, so I should see 3 loops. So from here I can deduce that the lambda is 0.8 meter, and therefore to find the frequency given the speed, I use V equals to F lambda. Frequency will be 375 Hertz. So this is not the lowest, because lowest, if you recall just now, we see 1 loop. This is 3 loops. So this will be the third lowest. There are 2 lower frequencies of stationary wave. The lowest frequency will be when you see 1 loop. That is when the length of the string equals to half lambda. So the wavelength will be 2.4. From there, I use V equals to F lambda. Frequency will be 125 Hertz. The second lowest frequency will be when you see 2 loops. So this is mode 2. The wavelength will be the length of the wire, which is 1.2. Similarly, use V equals to F lambda. I get the frequency to be 250 Hertz. Okay, with that, I'm done with the example on transverse stationary wave. Now I will give you another example of transverse stationary wave using microwaves. The setup is similar to what you have seen in general waves when you are finding the speed of sound or wavelength of sound. Okay, so here I will have a microwave generator. To get a standing wave, I need a reflector. So we have a metal plate here. You will need to adjust the position of the metal plate until a standing wave is formed. So how do you know a standing wave is formed? You use a detector. Notice this detector is not a microphone, because a microphone is used to detect sound wave. So what detector is this? This is a microphone. No, sorry, this is not a microphone. This is a microwave detector. Okay, so we just call it a microwave detector. And there should be some meter that indicate what is the intensity of the waves. So you have a microphone generator here. You have an incident wave coming in. You can see the continuous line. You can take that to be the incoming wave. The incident wave get reflected. So you can see this dotted line. Okay, this will be the reflected wave. So they superimposed. Okay, at one instant the wave will be resultant. So the position will be changing all the time, like that. Similar to that you see in the animation. So the standing wave will vary from maximum displacement, some displacement, zero displacement, negative displacement, and so far so on. So the detector will be able to detect where the variation in the intensity is, and from there you can find out what is half lambda and calculate the frequency of the wave, or just to find out what is the wavelength of this microwave. By the way, the speed of microwave, you know, okay, that is a constant. It is actually the speed of light. So if you want to find the frequency, all you need to do is to measure the distance between node to nodes. That gives you half a wavelength. And from there, using the speed of light, you can get the frequency of the microwave. In the next section, I'll be talking about longitudinal standing waves. And to illustrate this, we are going to make use of Kunz tube. I'm going to show you a video on Kunz tube. Okay, sorry, start again. The sound is quite irritating, so I'm switching it off. Okay, this apparatus here, right, which is basically a tube that is about 1 meter long with some fine powders inside. Okay, it's connected to a loudspeaker, as you can see here. Okay, this is actually a speaker. Then the speaker is connected to a signal generator. The signal generator can control the frequency of the sound wave. So when the sound wave is generated, it will cause the molecules inside the tube to oscillate. And because the powder, right, they are very fine, so they will be disturbed by the vibration of the air molecules. So this is Kunz tube in a closed tube. Why closed tube? Because the other end, right, is sealed up. So this add like a fixed end, which is the wall. Okay, so we are going to see what happens when the speaker is being switched on. Maybe a little bit of sound. Okay, he's adjusting the frequency. You see, this is the right frequency, and at this instant you actually see a standing wave. This is the mode 1 standing wave. The frequency is 119 Hz. Okay, next we are going to adjust the frequency to a higher value. So you can see the next mode of vibration. Okay, you can see one loop here, another loop here. So this is the next mode of vibration, mode 2. So the frequency is higher. In fact, it's 2 times the first frequency. Okay, we are going to adjust the frequency higher. This is the right frequency. Okay, now getting very noisy, so we off it. So this is the right frequency for the third mode. Can you see 3 loops here? 1, 2, and 3. So this is mode 3 of the frequency. Okay, I think we can stop here. And notice that although the fine powder are having maximum displacement, right, the air molecules here are actually not vibrating. If they are vibrating, they'll be pushing away the fine powder. So this point here is actually the node of the sound wave. Similarly, you don't see any powder here, right? That means the molecules are having maximum vibration. It pushes away the fine powder. So at this end, you actually see the anti-node. Okay, this end is actually the anti-node of the sound wave. Similarly here, this is another anti-node of the sound wave. This is also anti-node. Here, where you have a lot of powder collecting, this will be the node, and this will be the node. Okay, so like what I said just now, this is a speaker. Before you switch on the speaker, the fine powder or the cork dust, they are evenly distributed. Okay, this end is closed, sealed up, so the molecules will be vibrating. As you can see here, the air molecules are having maximum vibration, so it actually push away the fine powder. Okay, this one some vibration, so you have some powder. Here not vibrating, so all the powders are collecting here. So from here to here, if this is the length of the tube, then this will be a quarter lambda. Okay, because node to node, right? Successive node to nodes, this give you half lambda. So antinodes is in the middle of node to node, so the distance from here to here will be a quarter lambda, and a quarter lambda will be equals to L. That means the wavelength is actually 4L. So if I were to sketch the displacement distance graph, it will look like this. At one instant, then half period later, it will be here. Okay, so this is the displacement versus distance graph. Notice that you have maximum displacement near the antinode. Okay, the antinode not exactly at the end here, so that we have to do for some correction later, okay, which we call the end correction. So this is for closed pipe because this end is closed. Okay, the other end we can't close it because we need the molecules to vibrate when they receive the sound from the speaker. Okay, then this is node 2. If I were to sketch the displacement time graph, we have one antinode here, another antinode here, so this node. So this is how the waveform look like. At one instant, when the air molecules are at maximum displacement, then this is at the next instant when it's having the opposite displacement. So that will be that is half period later. Of course, there will be some other here that are not maximum, so some other timing. Okay, just now I mentioned end correction. Actually, if you look at the diagram, the loudspeaker is not placed exactly at the opening of the tube also. Then the amplitude also is it cannot be so precise that it's exactly at the tube. So there is this distance here, okay, that we actually cannot correct for experimentally. So in theory, what we do is, instead of just measuring the length, because the loudspeaker is here, the antinode is usually at where the loudspeaker is, right? So we call it end correction. So instead of the length of the tube, we take L plus E, and this is equals to quarter lambda for the first mode or the fundamental mode. Okay, I did another demo on the standing wave in a hollow tube. If you like, you can try at home, especially if you have organ, the open type of organ or the recorder. You can play the tune. Whenever you hear the sound, that is actually a standing wave form. When I'm talking to you, right, a standing wave is actually formed in my vocal tract. That's why you can hear me. Okay, there are some that cannot produce sound because a standing wave couldn't be formed in the vocal tract. That's why no sound is heard. Okay, what happens if you have two ends open, like the open pipe or open organ, or in the recorder? Okay, this is actually two ends open. The end that is open, right, is actually a free end. That means the molecule will be free to oscillate according to Newton's third law. It is not fixed, right? So free. So if it's a free end, it will be an antinode and antinode when a standing wave is formed. So if I were to sketch the diagram with an antinode and an antinode, the lowest frequency that you can have, or the longest wavelength, will be when the length of the tube, right, is equal to half lambda. Then go on to mode 2, same thing, you have the same boundary condition. This must be an antinode, this must be an antinode. The next highest or the longest wavelength will be when the length will be equals to lambda. Okay, then you can move on and on. Theoretically, you can go to infinite numbers. Okay, so with that, we come to an end of the section 2, which is on stationary waves.